Just a second. Okay, now I started your recording. Go ahead.
Perfect. Okay, hi everyone. I'm Carl from the University of Glasgow, giving the update on the MEMS assembly of the development and assembly of our MEMS gravimeter, also known as UNIGLA. So I'll be giving an overview on the. Well, I'll give a recap firstly on what we did previously in the last year and a bit. So basically what was from last time we presented an update on our side. I'll also give status updates on our hardware, our MEMS devices, and our assembly process, as well as what we have in store for the rest of this year in terms of assembly of our devices. So recapping on the previous update, we have been working with an external company called White Blue, who are based in Glasgow, for the manufacturing of our UNIGLA enclosures. So this includes the outer enclosure that houses everything in our system, our internal components such as our leveling mechanisms, our feet adjustments, our thermal enclosures, all that sort of stuff was all handled via them. So they were at the time in process of getting 25 of those systems made up for us. We were also working with a PCB manufacturing company just based outside of Glasgow for populating our electronics boards. So I'll give an update on how that has went in a few slides' time. And we were also ourselves in the Glasgow team were assembling and characterizing MEMS devices that we had to work in collaboration with a company called Kelvin Nanotechnology, who manufacture our MEMS devices, to give them the feedback that's necessary to start mass producing UNIGLAs that we can then assemble for various different projects, including Newton G. But within all that, as Daniele highlighted in the last talk there were several COVID restrictions that were in place at Glasgow, which made it very difficult for us to work efficiently, which then led to many of the delays that Daniele had highlighted in this last talk there. But we were at least able to make some progress in terms of delivering devices. So we had one system, our rapid prototype, RP 1.1. So RP stands for rapid prototype. This was successfully delivered to INGV this year by Christian and Stephen of our group. And this was successfully installed at SLN and is running in parallel with an iGraph. And data on this is to be presented after this talk by Christian and Matthias. So I'll let them go into the details for that, which I'm quite looking forward to. And just to give you an update on what RP 1.1 is, as it is still running. This is an early prototype version of our UNIGLA device. This is a picture of it in the top right here. It utilizes magnet wires to control the temperature within the system, as well as our MEMS communications. I mentioned that because I'll highlight it further within this talk, but this is just an example of what the internals of the system in terms of its wiring can look like. So quite packed. And our MEMS device itself is housed within a dual foam enclosure for temperature stability. And that's attained by utilizing 6 temperature sensors throughout the enclosure and various heater pads via closed loop PID control. So yeah, that's just to give you just to give you a recap there before the data talk after this for what RP 1.1 is. So where are we in terms of the hardware as of now? So we have successfully acquired all our Ouija enclosures from White Blue. So this is a photo of all our enclosures and storage in our building just now. So this includes the outer enclosure, the internal components such as like I said, the leveling mechanism, your manual feet adjustments, your step motors, your brackets, heater pads, temperature sensors, everything. That's all been delivered now. So we are in possession of all that. And each Ouija itself, we decided would come with its own individual transport case. We were toying with the idea of having two devices per case, but we decided to change that to just having each case individually house one system. That means that we can then include space for the cabling, as well as any sort of tools and stuff that we want to pack into each component to aid with installation of the Ouija systems at the site. And we also thought it would be just easier for general transportation if each if each system had its own case. So yeah, we currently have all them. Just to highlight a couple differences between the new systems that we have and RP 1.1. So on the left hand side here, you got RP 1.1, and on the right hand side, you got our new final Ouija devices. So RP 1.1, the enclosure is made of a 3D printed material, which is not IP rated. So water can get in, moisture can get in. Is not airtight in any sense there. Whereas our final systems are IP67 rated, which means that we can now take it outside into the field, which is very good. We also, with our new system, new upgrades that we made, like I highlighted before, we used to use magnet wires for our temperature controls and our MEMS communication. We no longer do that. So on the left-hand side here is an old photograph of our thermal enclosure. So you can see you got your first outer layer here. And you can see on the left-hand side, we've got a bundle of about, I think it's about 14 to 16 wires coming out on this side, and on the opposite side, another set of wires that are coming out. So these are the wires that were used for temperature control and MEMS communication. But as you can see on the right-hand side, we have now replaced all those wires. So now we just have one wire that comes out. It's just a grounding wire to ground the boxes. But on the right-hand side, instead of wires, we have a ribbon cable off the shelf component that we just bought for the MEMS communication. And on the left-hand side, we have a custom-made flexible cable for all our temperature controls. So this ribbon cable on the left is attached to all our heaters inside this foam enclosure, as well as all the temperature sensors as well. And what this does is it aids the robustness of the system. So no longer, if we have a broken wire somewhere in the system, we have to find it, we have to either fix it or replace it, which can be very time consuming. Now, if anything were to go wrong, you would just replace the ribbon cable itself, which we have quite a few in stock, including spares, just for that situation. And it also aids in the assembly because we no longer have to make all these pairs and bundles of wires that have to be labeled, then soldered and heat sunk and then all that. we can just do all that with just our little flex cables that we have in our system now. So that is a good upgrade that we've made to our systems. Now I'll go on to talk about our electronics of the Ouija. Below is a snapshot of a previously presented Gantt chart, highlighting various different aspects, but I'm going to focus on the electronics here. We have, like is highlighted before, we are working with a company called European Circuits, based just outside of Glasgow, for populating our electronics boards. However, they themselves faced a delay in populating those boards due to, I'm sure quite a few of you might know, it's a worldwide shortage in ICs, as well as just silicon in general, which is used in pretty much all electronics nowadays. So that kind of pushed their predicted delivery date back by a few weeks. So I updated that Gantt chart to highlight this. So it's the second line from the top. We expected them to deliver our boards by mid-September, which was originally, it was mid-August, so that's pushed back by quite a few weeks there. However, upon delivery of those boards, it wasn't plain sailing. So the aim of going externally to get these boards populated was to, rather than do it ourselves, is to go to somewhere where they would have a production process in place, and that would include a supply of ICs, which we then found out they themselves faced delays. But what we didn't expect was that several of the ICs would just straight out not work. So there were 4 ICs per board. So I'll say again. We got 10 boards made, and 4 ICs per board were not working, and they were all the same ICs in every single board. However, this was not straight away obvious due to another issue where when we would attach our electronic stack together, it was actually damaging our FPGA boards. So it was a case of solving one issue to then discover the real core issue of the system. So this was mainly carried out by Abhinav and Chris. They both worked very hard to come to the root cause of why the boards weren't working. And just to give you a comparison, this photograph on your left is a picture of one of the non-working IC components, and the picture on the right is one of the working IC components that we have in Glasgow from one of our other boards. And as you can see, there's some various differences with the way the symbols are printed, as well as the font size and the color of the writing and whatnot. So we suspect that European circuits were supplied with just non-working components. And this, like I said, this was a delay that we didn't expect to happen, but we did come to the root cause of it. We have a plan in place for how we're going to solve this for the 10 boards that we have, mainly that we have ICs that we can use to replace the non-working ones, and this will be done in-house by our electrical technician, who I think is currently working on changing some of these components out. So this was a very lengthy delay that wasn't expected. And like I said, we also have a shortage in FPGA boards. So like I said, we had a few that were damaged during the previous assembly with the boards that were populated by European circuits. We therefore had to purchase some more. However, again, there's not a worldwide shortage in electronic components, including these FPGA boards. So there's two variants of the critical snickerdoodle board that we utilize. One is a top variant, where your Samtec connectors are at the top of the board, and the other one is the one where it's at the bottom of the board. Now, we utilize the one at the bottom. However, there's absolutely none of these in stock worldwide. We went to all the suppliers. Went to Abhinav went to Critical themselves to find out if there's any in stock, and they don't have any at the moment. So what we did find though was a top variant stock with one of the suppliers. So we basically bought all their stock in the top variants, and we are getting the Samtec connectors moved from top to bottom. So that's being done externally again through European circuits. They have done one board for us just to check that it's possible to do, and this does seem promising. So we have other boards that we're handing over to them to get these connections moved from top to bottom. And we are also designing our own board, but this is not something that's going to be implemented in any of the imminent systems. So that's still a bit down the line. But that, if we have our own board, that will help us avoid the mercy of the current worldwide shortage of silicon components. So moving on to our MEMS. Like again mentioned previously, we were working under some very strict COVID restrictions, which meant that we weren't able to access the facilities as easily as we could that are integral to the work that we do. Mainly, it's the James Watt Nanofabrication Center, it's a JWNC, as well as the physics department, where we are based in. So yeah, like Danielle highlighted before, there were some severe restrictions in place where there were capacities on how many people can be in one room. This capacity was mainly just one person per room. When it came to JWNC, you had allocated time slots that you could only work to, and those time slots were limited per week, which meant you couldn't be in as often as you would like to. And in the physics department, you had another booking sheet for the labs, and you had to make a rota for who can be in at what time. However, at the start of October, so at the start of this month, booking restrictions were lifted from the JWNC, which means that we don't need to book in anymore, which makes it a lot easier for us to gain access to that facility. There is still some capacity restrictions in place, but that's something that we can work around, which means that we can now release, characterize, and assemble some devices, hopefully in the next few weeks and next couple months, to the point where we have a good stock of devices in place that we can use. So we currently have 10 samples that are ready to be either characterized or assembled. This is 10 more than when I presented the last update. So we are at a point now where KNT, who we're working with, are processing several wafers for us to get us more devices, because we're showing a bit of consistency in how they're made now. So like I said, in the next few weeks, we would hope to get some of those, some more further assembled, as well as characterized as we receive them. And like I said, the assembly of those devices is carried out by ourselves in the Glasgow group. There's a picture of Richard on the right here, doing some of the assembly process in the JWNC. So we assembled the MEMS layers. We also packaged the MEMS into its little ceramic packaging, while KNT do the actual processing of the wafers. But we do have to go externally for the wire bonding of our samples. So we go to the University of Strathclyde to do this. So just across the city, not too far away. I think we have some that we are looking to get wire bonded this week. And once they're wire bonded, we can seal them ourselves back at the physics department in Glasgow. So like I said, with greater access to facilities and a bit more consistency in the samples that we're receiving, we fully expect that we are going to increase the amount of available samples within the next couple months. So for example, I would hope that by the end of this year, that all 10 that we have in stock just now should be at the stage that they are ready to be sealed, as in all the wire bonding has been completed, or that they are ready to be wire bonded after the Christmas break. So I'd be very optimistic about that happening for the ones that we have already. One of the other upgrades that we have on the current MEMS devices that we're receiving is that we now can magnetically actuate the system, so the proof mass itself, which is not something that's available on the RP1 sample. So I've just got a little video here just to show you. So your blue signal is your drive, which is fed into the system, and your green and yellow are the actual outputs that we get from our system. So via magnetic force, by basically just changing the current that's applied going across the MEMS flexures, we can change the position, as you can see there, of the proof mass itself, which is very nice because it allows us to fine tune the MEMS to its most optimal position. And it also has a possibility of using this technique for reading out the signal from the system. So just for example there, nav is changing the current and causing our proof mass to move. So you'll remember that the yellow was previously at the top in this region and the green is at the bottom, and then it flipped, just showing that the proof mass has moved across fringe. So that's just a nice example of one of the upgrades that we'll have in all these MEMS devices coming up. So stop. There we go. So again, looking at the current status of UIGI assemblies. So we have two rapid prototypes that have been developed and delivered for deployment. RP 1.1, which was mentioned before, is SLN as part of Newton G. And we have RP 1.2, which is at Birmingham, down in England, as part of the Quantum Technology Hub for sensors and timing. So on the right-hand side, this is myself and Abhinav at Birmingham. You can see RP 1.2 in the corner there. And the Birmingham teams look to do some field trials out with this system, with its big brothers, its CG6s and CG5 in the background there. So that's exciting. And we also have one IP67 rated enclosure UIGI that's been assembled. So this system has actually been going through various indoor and outdoor testing the past few weeks at various locations around the UK and Ireland. And the goal of these tests is to learn the performance of the upgrades that we made, such as the flex cables, the different electronic configurations, as well as a thicker thermal enclosure that we have around the MEMS package. And this is also the first time that we've taken a Ouija system outdoors in unsettled weather. So for example, out in the rain and wind, which is one of the main tests that we've been looking forward to doing for a long time, because previously we'd be limited as to when we could take the system out in the, outdoors. It would always have to be a nice, calm, sunny day, or just not raining, which is very hard when you're living in Glasgow. So yeah, we're at the point now where we have this system, we're doing some tests, and we look forward to doing some future tests with these systems before we would then send them over to INGV for installation at Etna. So, like I said, we have 10 samples in stock. So 10 MEMS samples. This is a picture on the right-hand side of 3 of our samples that are ready for wire bonding. So like I said, these are the ones that we're hopefully going to get done this week at some point. And then sealing will happen soon after. Considering the unexpected delays with the electronics that we didn't foresee, so the non-working components and the debugging time that followed on after that, we are setting a goal of getting the device by the end of the year to INGV. So this would be one of the IP67 devices that we have. There is the possibility that we can also deliver one of the spare IP67 enclosures that we have to replace the enclosure that is currently on RP1. So these are some of the spare ones that we have in the bottom right photo here. That would mean that if we do replace the enclosure on RP1, we could then make it IP67 rated, which means that you could then potentially take it out of SLN and put it to one of the installation sites if desired. The only thing to remember though is that none of the internal components would change. This would just be a straight up change of the outer enclosure itself. So that's something that we can do when we deliver the next device to Catania. And just before we end, this is just a timeline for the remainder of the year for what we are looking to do. So we have this red line, that's where we are just now. So we have samples that are ready to go away for wire bonding. We have samples that are ready, samples that we're looking to assemble this week. So it's assembled the MEMS layers together. But we have one big grade out period here, which lasts over 2 weeks. So you probably know that COP26, the UN climate conference, is being held in Glasgow next week for 2 weeks. And this has severely affected the area around the west end of Glasgow where it's being held. So there are various different road closures. The university is advising that absolutely anyone who can work from home should work from home due to the delays and closures that are currently in place around the West End. So this includes personnel that are affected, such as myself, and potentially some other members of the team, as well as the delivery of any orders or components that we put in. So we just added in this little two-week grey period just to highlight that there could potentially be a slowdown in the work that'll be carried out in that time due to COP26. So just to conclude, we have, despite all the COVID restrictions we have in place, we have made progress this year. We have all the hardware that's required for assembly of our devices now. So this is now all down to us. We did experience delays in our electronics board population due to ICs that were dead on arrival. We have something in place to solve this, and we are currently in the process of getting all those boards fixed. As well as our FPGA boards that we ordered, they're currently getting modified, well, linked to get modified soon as well. And yeah, assembly of our devices has started. We are putting together some of our thermal enclosures with the flex cables. We also have MEMS that are ready to be wire bonded, as well as assembled. And like I said, we'd like to have one of our IP67 data systems sent out to Etna by the end of the year, with the possibility of then replacing the enclosure on RP 1.1. But RP 1.1 is currently taking data at SLN. I think it's still taking data as I speak. And this will be presented by Chris and Matthias, I think now. So I'll stop sharing my screen. I realize I've went to right up to past. So I think if Matthias or Christian, if you're ready to share your slides.
Maybe a question first.
Yeah, for sure.
Yeah, is there any quick question for Carl? Yeah, we can move to Matthias or Christian, and then questions maybe can be also asked during the break.
Okay, then I will share my screen. Good morning, everyone. My name is Matthias. I will share this presentation with Chris, and we're going to be showing you the first results from the UIGLA that is currently installed in Etna, which I think is a very nice milestone for the project, because it's the first of many to be installed there. So just to summarize what Carl just showed us, this instrument, it's a low-cost relative MEMS gravimeter. I think it's important to emphasize that it's low cost. It costs a fraction of traditional, conventional relative strength gravimeters. So that is a really nice thing if we want to deploy many of them and increase the spatial resolution of gravimetric data used for volcano monitoring. So this thing was developed by Glasgow, and it's one of the first deployments in what I call the field. So it's in another project. They gave us the instrument to install, and it's operational now. The data logger is based on a Raspberry Pi, so that reads out the MEMS gravimeter. That's based on a custom PCB as well. It's responsible for the time stamping and readout of the instruments and data storage and telemetry, so getting the data back to us. And it samples at a frequency of 1 Hertz, so it has a low sampling frequency. And there's a couple instrument channels that the UIGLA has. Of course, there is the vertical component of gravity that it reads out, but there's also important channels that concern, for example, temperature. They have 6 different sensors, temperature sensors in the enclosure and near the sensor, because temperature is, of course, a very important channel when it comes to gravity, because one may influence the other. There's channels for tilt, so we know whether we're reading a component of G, and there's also channels for pressure inside the instrument and humidity. So we all have these numbers. And the UIGLA is installed here on the southern flank of Etna at Serra la Nave, which is the Royal Astrological Observatory. It's shown here on the map on the left. And the AQG is also illustrated on the map, which is the little triangle there, which is a bit closer to the summit craters of Etna. So the AQG is, I think, maybe 1 to 2 kilometers away from the summit, and SLN is about 6 kilometers, but it's still close. And there's there it's installed in the basement of the observatory, so it's in a sheltered environment at the moment with a constant temperature. But there's one particular nice feature about this installation site is that it has a iGrav installed there. So these are 2 pictures or photographs showing how the setup is right now. So you can see the Ouija here in the corner in this insulated box, and the Pelican box with the PCB and the data logger there, and of course the iGraph there besides the Ouija. And the data logger is quite powerful because it allows for remote communication with the Ouija. So that means that, for example, the team from Glasgow can interact with the instrument, change some settings without having to be physically there. So that's a very big plus for us. Then about the deployment itself, I said it was installed in the basement of Cella Nave, and it's been operational for a bit less than 2 months. So it's been running since the start of September. And the best thing about this place is that it's co-located with the iGraph, superconducting gravimeter. And essentially that instrument is drift-free, so we can use the data from the iGraph and compare it to the Ouija and use it as a reference, because what the SG records is essentially the real true gravity signal. But if we didn't have that, we could of course have used a theoretical tidal model to see how the Ouija performs. But now we have the actual signal, which is a great thing because we can look at the residual between the two, for example. And this gives us the opportunity to characterize the performance of the Ouija, look at some characteristics, maybe drift, or whether the calibration is right, all that sort of things. So I'm going to show you the data from that soon. And of course, we have the possibility of remote connection to the Ouija to restart it and reconfigure it. And it's been operating continuously and autonomously. So no one's really been interacting with it much outside of some details. And there's barely any gaps in the data. So it's been running for 2 months quite well without any significant problems. So then the first data, I think this is of course the most exciting part to look at. Well, there's a couple of things that are immediately obvious from this figure. So the y-axis is expressed in microgals, and then on the bottom we have about 1.5 months of data. You can see that there are some big tears in the data, which is not unusual for spring gravimeters, of course. And these two tears are on the order of 10 microgals here and there. It appears to be a coincidence that they have the same size, and the second one seems to undo the first one. And there's a smaller tear here, about 100 microgals. And the reason for these tears, we don't know for sure, but we have 2 reasons they could happen. For example, maybe one of the wires or the connectors in the instrument is a bit loose. That's causing a jump in the signal. And an alternative is that there is the material that's keeping the sensor upright. It's got a bit loose, so that means that the sensor itself tilts a little bit. So you're reading out the component of G, which also causes a jump in the signal. So we're still looking into the reason for these jumps. And if it's caused by a faulty connector or a wire that's not connected very well, then the instrument would need to be serviced by Glasgow. So that's not possible to do remotely, of course. And in the middle, we see a very nice teleseismic arrival. So it's, well, the gravimeter is an accelerometer as well, of course. But it's nice to see that in the data. So what we can do, of course, is remove the stairs from the data by just adding the respective offset, estimated offset, because we have to do that by hand. But what we see in the data is this long-term residual drift of quite a high order. Just mark that there with the green line. And that is something we obviously want to remove from the data, because we expect that it's not a real gravity signal, but it's more of an instrumental signal, whether it's settling in its new position or there's kind of throw or tilt. So there are some classical signal processing steps that you can take. For example, I'm showing here removal of some orders of polynomials from 0 to 4. And of course, you can see if you increase the order of the polynomial, you can get the data close to more close to being flat. So you're eliminating some kind of high order signal from the data. And of course, you can keep increasing the order of the polynomial until 12, but eventually you got to stop doing that and well, take a look at the rest of the data. But this is, of course, the first step we need to take in order to get rid of the really long-term drift. And if you look at, of course, very or smaller segments of the data, you could use lower order polynomials because over the course of this 1.5 month, there's a lot of variation, but it's on smaller segments, it will be much less. So the green line on this figure is what's recorded by iGraph data. So the nice thing about the installation is that we have the true reference for what we should record. And the blue data is the Ouija data, the raw data. So I've not removed anything from that yet. So it's just what comes out of the instrument. And you see that there's, of course, a big difference. But if you do some signal processing, you can get these two very close, in fact. So this is with a low-pass filter applied to the data. So instead of seeing all this high-frequency noise, we just take a look at the low-frequency signal that's present in the data. And we plot it against the iGraph data again. And you see that the tides are now clearly visible in the Ouija, except this high-order drift is still present in the data. And there is a residual between the iGraph and the signal recorded by the Ouija. So if I take a look at a much smaller segment, so I really try to eliminate all this drift by just taking a smaller segment and then using a very high order polynomial, you can see that the Ouija actually very accurately observes the Earth tide. So I think this is very impressive to see, although the Ouija kind of overestimates the tides, it appears from this figure. But that might be because the calibration of the instrument is not completely accurate anymore after the travel, because we don't know what effect traveling by air has on the instrument. So it's important to make these comparisons between the either theoretical tides or observed tides and the instrument to see if we need to make changes to the calibration or the gain of the instrument. But I think it's really impressive that that this is the data that's recorded and it matches very closely to what the iGraph records after some signal processing. So the gravity residual is important, and it may have some causes. We expect that it's probably due to response to thermal changes, so changes in temperature in the enclosure or in or close to the sensor. There's of course also the tears that we saw in the data, and this small tear of 100 microgals we expect it was caused by a short circuit in one of the temperature sensors. So they just completely dropped to minus 150, and it's not reading out the correct temperature, causing the system to constantly overcorrect for this faulty readout. And the large tears, as I said, we're not sure what it is, but we suspect it's a wiring issue. And the similarity of the magnitude, this 10 microgals for jump down and jump up appears to be a coincidence so far. So this is the important slide. It shows the gravity signal at the top after some low-pass filtering and removal of the long-term drift. And at the bottom, we plot the enclosure temperature, and that's been subject to the same processing. And when you do a correlation analysis between these two signals, what you see is that they have a very high correlation if you shift the temperature 30 hours into the future. So it appears that temperature is leading a change in gravity, although this 30-hour time constant is suspiciously long. We don't know why that there is a change in gravity after 30 hours. You observe something on the temperature channel inside the enclosure. So this is still a mystery, but it appears to be one of the main drivers behind the long-term drift. And there's of course some things you can do, because if you know this correlation, you might be able to correct for it. For example, by just looking at the gain between the temperature and the gravity, then subtracting that from the gravity using the temperature channel. So this is one of the challenges that we still face. This just shows you the power spectral density for the WEG data and a broadband seismometer very close by. I think it's about 50 meters away. I know some people are used to the what is it, Allen variance, Allen deviation, but I'd like to show the PSD. And these gray lines are the Peterson continental noise models. So what you see here is that the noise floor of the WEG is about minus 120 decibels. So that comes down to about 100 microjoule per square root of hertz. I looked at this because I was interested to see where the high frequency noise in the instrument came from, whether that was inertial or instrumental. And if you look at this figure, it appears that the noise is instrumental because the ambient seismic inertial noise recorded by the seismometer is much lower here. And that's clearly observing the microseismic peaks here. So yeah, it tells us that the instrument records noise at this sensitivity. Then I'll just come to the conclusion of this first analysis, because it's of course an ongoing work. We haven't had enough time to look at all the data in detail yet, and there's probably still a lot more hidden in there. So the instrument has been operating autonomously without any significant problems for more than a month. So we don't have any gaps in the data, which is great when it comes to signal processing. And the WEG is, as we saw in the figure, clearly observing the earth tides. And if you look at either the power spectrum and you integrate in the high frequency band, or you do the same calculation in the time domain, you would find a standard deviation of about 70 microgauss. So that's a nice number to know about. I think it's a bit higher than we expected, but it could be caused by the effect of travel. We don't know exactly what the consequence of that is, so that's something we're looking at as well. And what is really apparent from the data is that the instrumental drift is for now a limiting factor in long-term observations, so over the course of weeks and months. Although this is, of course, a very important thing in volcano monitoring, looking at long-term changes. So that's one of the challenges we face now in the processing of this data. Although the drift that we observe may not prevent short period events like lava fountaining or something else to be observed, so it's not all bad. But I think the main conclusion is that there is a very clear coherency now between the observed enclosure and temperature inside the MEMS and the gravity signal, with a very strange 30-hour time constant or time lag, where fortunately temperature leads gravity. It would have been worse if it was the other way around. But it's still a mystery why this is happening. And I think this is my part of the talk, right, Chris?
Thank you, Matthijs. Yes, I'm Chris. I will talk a bit more about the technical provisions that we took to push and get around some of the issues that we see with the device installed on Etna. So I will share the rest of the PowerPoint presentation. So, of course, some of the challenges that we see because of these non-linear drifts can be dealt with. Well, one way you can deal with that is using machine learning, using time delay neural network. I believe Thomas King did some work on that, because these are shift invariants. So it's an algorithm that can see patterns in a time series and do a correlation. Or we could also regress against the tides. Although we are not sure what these changing drifts are due to, we have evidence that suggests that it's due to temperature effects. Now, although we do control the temperature of the MEMS to be within less than 1 millikelvin, that's just one sensor inside the MEMS package. So if there is like a gradient inside the MEMS package, that could cause changing drift. Of course, the plot that Matthijs showed before shows a clear correlation between MEMS drift and the enclosure drift. So that's a temperature on the electronics of the MEMS. So I will show in a bit how we got around that by remotely accessing the gravimeter to reconfigure the temperature control for the enclosure. So one, okay, another idea that INGV has is you can anchor the drift by taking the AQG on occasional surveys and see what the absolute gravity signal is for the MEMS. So what do we see here? Here we see on the second plot, on the middle plot, it's the temperature of the main enclosure, and before the arrow, it wasn't really controlled at a particular set point. So with remote access, we are able to establish temperature control to this level. So after this point, you will not expect the temperature drift that Matthias showed in the previous plot in the data, but we are still gathering more data to review this result, this correlation. Matthias also mentioned a short for a sensor. This is one of the sensors that is coming out of RP 1.1 to monitor ambient temperature. Now for the widgets that we have now, we won't have a sensor that's coming out of the enclosure because that will not make it IP67 rated. So what we think happened is that maybe the leads of that sensor, which is a PT100, touched and shorted. So we've seen that after this point, there was higher noise in the MEMS data. But that was because this short destabilized one of the other temperature sensors that we were able to correct. I will show this in a plot in a subsequent slide, which brought back the noise level, the increased noise that was caused by this short. So yes, one good thing about the widget is that it communicates using UR communication, using student data logger that INGV built. And we are able to this way send instructions, log in remotely to the Pi, and use Python scripts that are written on the Pi to change the temperature control or do some tilt adjustments if needed. And in comparison with RP 1.1, the new devices will also be more robust, as Carl mentioned. They will have flex cables, for example, rather than manganese wires, and temperature sensitive electronics. We are pushed deeper inside the thermally controlled box. Yeah, it's important to stress that this first device on Etna was a rapid prototype. Our benchmark, one of the main benchmarks for success for the Glasgow team was to see what effect the transit, the installation will have on the MEMS between for this prototype between working in our labs and then working on Etna. And the fact that it's able to monitor tides and we can correct for any issues that we see, such as for temperature control destabilizations. That's good. So this is an example where we use the Raspberry Pi and one of the Python scripts to change the temperature set point of one of the sensors that got destabilized and raise it to a different higher set point. Yeah, this capability will remain for each individual WG that we send to the field. So for each device that we send, we'll need to do an initial recalibration to see if to adjust it for tilt. to make sure that the MEMS sensor points vertically to gravity, and then to do to thermalize the system before we connect it to the INGV network. And yes, the next plan with the multiple with the next batch of widgets that we'll be sending on Etna will be tested not in the bunker that the prototype is, but outside in the harsher conditions where in the winter can get very cold and in the summer very hot. So yeah, that's we are looking forward to send these new devices and see how they will perform in these changing environmental conditions. On behalf of Matthias as well, thank you. And if you have any questions, ask.
There is a raised hand by Michel Van Kamp. Do you have a question, Michel?
Yes, thanks for the talk, and I'm looking forward to seeing the future results. I just wonder if you interaction with people like Duncan Agnew at Scripps or the colleagues in Germany at Black Forest Observatory, because they could prevent you to some extent to reinvent the wheel. I don't know, because a lot of your problems with thermal controls, I suppose they are well known by those people or even manufacturers. So I don't know. And if you have no contact, I suggest you to contact them.
Okay. Yeah, some of our problems are because we use multi-layer temperature control. The new devices, the widgets that we have actually have better temperature control when we are taking them out for surveys in around the UK and Ireland. We are able to just turn on the temperature servos, and all the temperatures layers would settle at the temperatures that we are expecting. So at least that's a notable improvement between the prototype and our current devices. But yeah, heed your advice and see what other people in the industry deal with these issues.
Okay, thank you.
Thank you. Thank you very much.
More questions? René and Giles. So who wants to? You just came together. Maybe first René and then Giles. Or Giles, do you want to comment on the previous question?
No, I think if René wants to go first, that's absolutely fine.
Okay. René, you are muted and we cannot hear you.
Yes, now you can hear me. Yes, a very good presentation. I'm myself in the gravity field measuring, and I know Matthijs from my work from my university. I saw Matthijs speaking about the TARS, and it was not really known where they come from. Is that correct?
Yeah, so we have two hypotheses on why they're there. So one of the reasons is maybe because one of the wires is a bit loose, or the connectors, and the other reason may be that the sensor itself is a little bit tilted because the material that keeps the sensor upright let loose. So you're measuring a component G suddenly, which causes a jump in the signal, but we're not sure. Yes.
Yeah, well, I recognize some of these things, and not known from the others. Matthijs knows that I'm working also on a device myself, and I saw some of these signals that they say, well, I recognize them. And one of the things that can happen with the TARS is that is the connection of the sensor sometimes inside, sometimes the connection to the housing. And sometimes you can have, I don't know how it is mounted, but with screws or something, and with a little temperature effect or a short vibration, you get a sort of, sometimes on one of the points, a sort kind of a slipstick effect. That you see the signal running and then it jumps and it comes back. I saw that the same with my device, and it was from that connection. You have to look to it. Maybe sometimes you don't expect it, and then still it is there. It's because you are measuring very sensitive signals, very small, that you start to see things that you normally don't see. So that is something to think about, to look back to how the sensor is inside is built, or how it is connected to the housing. Sometimes it can happen there, but because I see you also that you have some small change in the temperature, and that is sometimes already enough to do this.
Okay,
thank you. That was very informative. Yeah, we do think mostly that it could be due to a connection issue, maybe with the wire bonding inside the MEMS package, or maybe one of the analog carrying wires being a bit loose on the solder. Yeah.
Giles, you wanted, yeah.
Yes, yeah, thanks very much. Yeah, it's just a comment really, actually. So of course this 30-hour time constant between temperature and MEMS signal is very interesting. And it's just to add some thoughts there. So we don't think that's a sort of direct coupling, because whenever we change an outside temperature, it actually gets communicated to the MEMS enclosure relatively quickly, where relative means, you know, the order of minutes rather than, you know, tens of hours. So one thing we are looking at actually, which could be a possibility, is when we put together RP 1.1, we of course, when we close up, seal up the MEMS package, this device is sort of backfilled with the gas. One thing we didn't do here actually for RP 1.1 was we didn't actually long-term bake the system. So it's quite possible that temperature gradients are actually sort of causing some, maybe it's exchange of humidity within the silicon. So we're thinking that maybe temperature gradients are driving quite long-term time constants within the MEMS package. So in our next devices that we'd like to put together, we're certainly going to be either baking them for maybe 20-25 hours, like a day of baking, to try to drive out the moisture. Even better if we can bake them under vacuum and then backfill with a sort of dry nitrogen or argon is what we're using typically. Because some of my work in the gravitational wave community, where we work on building fused silica suspensions, we do see very long time constant there. So we see the quality factor of the suspensions vary over daytime scales. And that's typically as we pump out due to exchange of humidity with the fused silica. So it's possible that there's a similar mechanism that's changing the properties of the device. We also have the spacer layer, which is our readout, is a polymer photoresist, and that's also quite sensitive to humidity. So its thermal expansion can change. So all of these sort of long time constants could be coming from the package itself. So we've got a few thoughts about how to, you know, maybe make some changes and see if that improves the performance.
Thank you, Giles. There is a question by Francesca Silveri. Thanks, a nice presentation about the 30 hours delay. Since, if I got it well, you first apply some filters to the gravity data, and filtering can cause delay in the signal. I was wondering if you try different kinds of filters to check if the 30 hours delay is consistent.
Yeah, so like Abhinav, he said in the chat, it's the same filters are applied to both the gravity signal and the temperature signal. So I don't know if that's the reason for the shift.
Okay, then another question. Matthijs can confirm this. I think the same filter was applied to both. Yes,
That was the answer.
answer already. Yeah. Okay, we do have a break now for half an hour, and we are supposed to start again at 11:30. If there are other questions, we can, of course, continue discussing. Otherwise, we can pause the recording and the meeting and resume at 11:30. But if there are any more questions, please go ahead now. Daniele, you wanted to say something?
No, just that we will restart at 11:30 with the presentation by Vincent Menoret from XBlue about the development of field-compatible absolute quantum gravimeter. So we can take our coffee break now.
Good. Then see you later.
See you later.